Okay, so I'm talking about the Pilgrim Fault today, and the question is: has it faked it till it made it? Is it a fault that looks more regionally significant than it really is? And that obviously has important implications for how you might think about the structure, both within uh, the regional geological evolution of the inlier, but also in terms of lowering risk with discovery and exploration activities around it. Before I go much further, I'm just going to caveat this talk. I'm showing there a photo of some hot air balloons from Canberra, because there is a severe risk that there may be a bit of hot air in this talk. I have not done a huge amount of work on the inlier. When I was in Anglo, we were exploring south of Mount Isa undercover, and I've had a few students work on the region, including around the Pilgrim Fault, but I don't by any means consider myself an expert. So all mistakes here are mine, and but at the same time, hopefully that means that I come here with a little bit of a blank slate in terms of how I think about things. So why might we be interested in structures like the Pilgrim Fault or other similar looking features? Obviously, Jim's already talked about the Cloncurry Fault earlier today. Well, we know globally, when you look at other mineral systems, that subvertical steep dipping structures can have a first order influence on the spatial distribution of ore deposits. And here's a classic example from, I think that's the Porcupine Desta shear zone from the Superior Province, which I had a student work on, and I did some collaborative work with Nick Hayward as well. And you can just see with the image on the right that the shear zone is regionally extensive, and it has a first order spatial control on where a whole bunch of world-class gold deposits are formed. And the way we explain this sort of relationship is thinking about how faults behave in the modern day. So using the modern as a key to the past. When you have regional large main shock earthquakes on big scale, crustal scale structures, they can generate aftershocks and fracturing in their wall rocks, which is somewhat predictable from the stress and strain field that's generated by the slip on the main shock. And you're seeing the image on the left here is actually from the Landers earthquake sequence from between 1992 and 1999. And that was a major 7.2 earthquake. It triggered thousands of greater than magnitude 5 aftershocks, which are shown by the white points. And they are spatially constrained by what we call the Coulomb failure stress change, which is just an elastic stress change that you can calculate from the slip on the fault and the fault's geometry. And we applied this approach, this simple mechanics, to ancient fault systems, looking at orogenic gold systems, Carlin type epithermal systems, and using simple structural geology field data to constrain the geometry of large scale faults that are controlling mineralization. We extracted kinematics from outcrop, and then we ran the modeling approach, and you can see in these images in the top right that where domains of elevated fracturing and enhanced permeability in the crust are predicted to occur more frequently over time is also where the distribution of gold deposits are found in the grey polygons. And this technique works in 3D. So that's all well and good. Mount Isa is an interesting, I actually think of it as one of the natural wonders of the world. I just think it's the most spectacular, one of the most spectacular geological domains. And when you fly over it, not only is the geology very pleasing to the eye, but it's a world-class region that's host to many IOCG and sediment type sediment-hosted copper, lead, zinc deposits. There's pervasive evidence for fluid alteration throughout the region. You can find copper all over the place. Many fluid inclusions are hypersaline when we measure their chemistry, and we know from ICGs elsewhere in the world, such as this map on the right. This is from the Monteverde district in Chile, that the ICG systems in those parts of the world do appear to have a spatial relationship with regional scale structures, strike slip structures. In ISA though, the relationship isn't so obvious. Regionally, on the regional scale, it's enigmatic. Locally, we know that ICGs have a well-defined structural control, but regionally, it's very difficult to say. It's very difficult to use the same approach that you see in other mineral systems in terms of clearly relating mineralization to a particular structure and then working out the spacing dynamics of deposit location along them. So it raises the question whether there's a scale dependence to mineral system behavior, or whether we just have a lack of constraints and we haven't had time to explore the system properly. So you can come up with a bunch of questions, you know, for the Pilgrim Fault based on this context. You know, what are its structural characteristics and its dimensions, laterally and vertically? What are its origins? What can we say about its influence on crustal hydrodynamics? And these are obviously all related to understanding both its geological significance and its potential for discovery in the region. So very quickly, just let's step through some observations. This is a map of the Isa Inlier. The yellows and blues are the cover rocks around the Inlier. The Inlier is shown just in white here. And these are a series of some of the more significant structures in the region, which we know have had strike slip movement on them at some point in their history. And the Pilgrim Fault, as defined, comes up from the south here, and it intersects the Fountain Range Fault, and it possibly is continued by the Roseby and other structures to the north. We know as well that when you look at patterns like this, it's quite interesting that you can begin to see that there's a V-shaped distribution to some of these structures. And in this case, I'm just looking at things like the Fountain Range and the Pilgrim, and their late geometries as we understand them. But there's intriguing V-shaped geometry to the patterns of the geographic distribution of faults, which I'll come back to later. Based on this map, the fault itself is laterally extensive. So it appears to have a very significant regional distribution, and particularly if you link it up to the Mount Roseby and Kulala structures to the north. When you look at the gravity for that region, it's coincident with a strong gravity response on its western side. And various researchers have mapped the Pilgrim Fault to the south of Isa, and they've noted that it has had influence on Neoproterozoic and even Paleozoic geological history, with appearing to bound basins and control reverse and then be inverted and undergo more reverse movement, even into the Paleozoic. So it seems to be very significant regionally. Genevieve Lucatina was a master's student of mine when I was at UWA, and she was doing just a very sort of condensed research project because it was a master's by coursework. But at the time, she was working for Glencore MIM, and she was able to map the Pilgrim Fault here from about the Kalman deposit down to the south, down to around the Duchess area. And basic observations that in the field it appeared to be west dipping steeply, west dipping on from both foliation, quartz vein breccia outcrops. The mapping of the kinematics was very difficult, and to do it justice, you know, she really needed a lot more time to do the study justice. She really needed a lot more time, and I needed to have more time in the field with her as well to kind of work out the kinematics and structural evolution of this system. She thought she could see normal and reverse movements, early normal and reverse movements on it, but then there was clearly a strong sinistral kinematic to the system. The fault itself is located on the western margin of the Mitakuldi culmination, this big complex fault structure to the east that I'm just showing with my laser pointer. And across it, there's a change in stratigraphy, that a distinct stratigraphic age where even though these are kind of correlative, the stratigraphy on the left is 20 million years younger than that to the right on the east. It has been defined as a terrain boundary and as a boundary between the eastern fault belt and the Mary Kathleen domain. And if you follow that, the structure along strike, then there's a lot of mineral occurrences on its potential northern extension. And into the south, not so much, although you can note there's an asymmetry to the mineral occurrences, with the majority of mineral occurrences occurring its western wall. And the other thing of note, classic paper by Rubenak, is it's a boundary between amphibolite and green schist facies grade rocks. So you can see here, here's the Pilgrim Fault again, the Fountain Range Fault, and Mike Rubenak mapped out dioxide-related calc-silicate facies here, but it jumps across to green schist on the east. But it's not a precise boundary because you can see little slivers of the high-grade rocks on the eastern side as well. What can we say about its influence on crustal hydrodynamics? Not a lot, but it has been hypothesized to be a control for regional sodic, calcium, potassium metasomatic patterns. Here's a map I just stole off that was publicly released by Cullen Resources, where they're showing Pilgrim Fault underneath cover, where they predicted to go underneath cover, and apparent spatial association of red rock alterations associated with where that fault is expected to be. But regionally, we find red rock alteration all over the place. It's not always clearly related to any kind of structure, and it's one of those enigmatic wonders of the world that is distinctive about the Mount Isa inlier.
That's 2 minutes, Steve.
Thanks, Karen. So just drawing to a close, I've started talking about the Pilgrim Fault, but what I'm actually going to end up talking about is an entirely different structure. And this is work by Karen. I think when we take questions at the end, maybe Karen can answer many of them. But this is based on her most recent seismic interpretations. And we're looking here at sections through seismic line 06GA M6, just to the south of the inline. There's the Pilgrim Fault going through. And where the Pilgrim Fault is projected to go, it's very difficult to find any evidence that it is as regionally extensive, vertically extensive as it appears to be laterally. In fact, the most important structures that Karen's picking out are these low angle features. And there's one here which is she's named the Black Mountain Thrust, which if you can trace in other seismic sections, and this feature actually peels into the Pilgrim Fault. What can we say? The fault appears to cut the nose of that thrust. But the interesting thing about it is that thrust geometrically seems to be the superbasin sediments are shown in the eastern fault belt here are thickening sort of towards that. So it implies it's indicative that maybe this low angle feature has a very early history and was once an extensional feature, basin bounding feature that's then been inverted. But interesting, I want to point out is how the Pilgrim Fault cuts its nose. Because, oh, before I get there, the seismic interpretation is also corroborated to some extent by the MT, where we can see this interpretation from Karen coincides with some of the MT conductive anomalies we see at depth, which are bound by the structural geometries. So interestingly, if you look at this in map view, here's the Pilgrim Fault tracking up to the north where it intersects the Fountain Range. Here's the Black Mountain thrust that Karen is now interpreting. And that sits in a stratigraphic and geometric position that's very, very similar to the Belonga thrust that Mark O'Day mapped in collaboration when he was a student of Pete Betts. So here's a map from Mark O'Day's paper. Apologies, I can't quite remember when that was published. I failed to put it on here. But the point is that the Pilgrim Fault, as shown in the seismic, is cutting the nose of that thrust. And if this Black Mountain thrust is the same correlative feature, then that suggests that this thrust is actually a regionally extensive and very important feature that's coincident at the surface with where the Pilgrim Fault's just coming through. So just concluding, I haven't had much time to really explore this in detail, but some of that V-shaped pattern makes me suggest that there's some tectonic analogues to the region. If you look at places like central Iran or the Tibetan Plateau, which are intracontinental deformation zones distal to the plate margins, but still being affected by plate margin tectonics, then you often see V-shaped strike-slip fault systems developing coevally in a contemporary way with thrust belts, and there can even be localized rift basins forming. And we see maps here of the Tibetan Plateau showing exactly that. This is the same area, just highlighting the V-shaped structures with focal earthquake mechanisms, showing that most of the brittle deformation forming on these structures is only in the top 15 kilometers of the crust. So to conclude, bunch of ideas I'm throwing out there. Pilgrim Fault's really part of what appears to be a laterally extensive V-shaped strike-slip fault system. That's that much we can say confidently, but vertically it's limited, particularly in seismic. To my mind, the model at the Pilgrim Fault as a terrain boundary is not really supported by the seismic, and there may be some analogues with modern day regions of continental distal convergent margins. So I've started out talking about Pilgrim Fault, but really the structure I want to highlight is this one. The Belonga Black Mountain thrust system is a regionally significant structural boundary, which is partially hidden by the Pilgrim Fault. Based on what Pete's just been talking about from Mount Isa itself, is there an analogy with this geometry with what we see at the Peru Mount Isa geometry? And I can't go into the field evidence, but Mark O'Day suggested the Belonga thrust had an early extensional history, and that's certainly something that the seismic seems to be supporting. Thanks very much. Excellent.
Thanks very much, Steve. Appreciate that. And I really enjoyed that, because you've brought in some different aspects to what I've been thinking about.